So instead of just doing normal shower, we're just all straight up. Have them where there's 3 completion points along the ground.
Nice.
I remember you guys saying you were doing that.
We're just doing straight arms. You do that when they walk up.
Originally, it was just like
scowl at them.
with some holes in the bottom.
And honestly, like,
But now, we have to remove it because
Yeah.
and we want it like it's a lot. So.
I was.
It's only
So you
two
guys
questions.
copy and read it.
First
Actually,
one
I
is 60
found it
points.
first.
So
So,
it's like a big food body
I didn't see
energy problem. It's like find an natural frequency and solution with like fat equivalent mass.
You guys just came to the same conclusion.
Well, that was my
It's a little
OG.
tricky.
That was my
Was it that, right?
Yeah.
Weird.
Well, technically, it was in my
Yeah. So the middle one only rotates. And
Oh, yeah, I don't
bracket
think
has 2 different
a lot
rings.
of them are going to show up.
Yeah, he also
Given
said
that
he'll be 20
data,
minutes.
you need to back out.
Well, he's going to miss the one part that
This
he's
is
going to
the
be like,
it was right.
this
And
data.
then
yeah.
So it's just a lot of like deriving everything in terms of the what you're
Sorry, that was really bad. I feel.
then it's not too bad. It's just
Be recording.
Hi,
Derek. Hey.
Do you have your equipment by chance?
Sweet. You just need to find your
Where was,
That one's like less obvious.
Wonderful.
No, absolutely living the dream.
No, I'm flying.
Oh, same. When I was at work, they'd be like, "Oh, how are you doing? I'm living the dream." I was like,
Alright.
"Hi." I was living the dream. I was like, "Here."
I have a camera going right there, so.
Oh. We're gonna move.
It's actually just recording.
No, where's my iPad? Aww. And
You had it in your hand.
This is football.
Up there.
Derek.
Ooh, that was Chris.
That
That was so nice.
I think it got a little bumped up in the front.
Okay.
It was good. It was good.
Hey guys, butt to the right.
Two things.
Butt to the right.
To the right.
To the right. To the right.
Butt to the right.
What should you?
Everything you need. Isn't there
I hate y'all.
To the right.
What's the heat transfer on the airplane?
In the closet. Not that
It needs to heat it up.
Oh yeah, not that.
It's not a driveway, we can't figure it out.
I was like,
I was like, sorry.
Dark.
Yeah, it's not a driveway. We
All right.
can't do a heat transfer. Oh, sorry.
You're at
Noon.
That's fine.
To look at.
We haven't that actually that one idea. Every single one in this team. Yeah.
just fine.
Just vibe.
yeah, tell him. No, actually, no, just walk in with us when we walk into Panofsky and everyone else is taking the test, and then you tell him that we can start the test later. Like walk into the vibes, and if we say you have to come with us to talk to Panofsky.
Yeah, I don't like that part. I don't think I can do that. I'm a little slow.
That's small. Isn't really learning to this. But the other day I was talking
Like,
this morning
we can
actually.
team
I was
sending.
like, why don't you
Yeah.
just do this with like a threading mill in the middle? I'm like, oh yeah, just do like a G91 and an interpolation with the feed down, and then just talk to the G code. And I was like, what?
Okay.
And then actually, circular interpolation. You know, and it's go time.
That's the last word.
Yeah.
You said give me a reaction. They're talking.
Is it okay if we start without Dr.
Should you just postpone the presentation?
So Adams is not.
I
I'm
think
okay
this
with
is
that.
So Adams is not arriving?
He's just not here at the moment.
Let's just go with that.
It is.
We
Well,
should start.
Yeah. I'm so small next to you guys.
Are we starting without?
I can't send them the video. Do you want us to like?
Yeah.
Okay.
Hello everyone, welcome to the Critical Design Review for Corvus. I am the design team lead as well as the responsible engineer for the nozzle analysis, Brianna.
My name is Winona Ralston. I am the responsible engineer for the solid analysis.
My name is Kevin Sweet. I'm the responsible engineer for the liquids analysis.
I'm Finn. I'm the responsible engineer for the ground hardware and the igniter sections.
My name is Isamibo, and I am the responsible engineer for nozzle, CAD, and manufacturing.
My name is Noah Kane. I'm the responsible engineer for the stress analysis on the engine as well as the solids CAD.
My name is Joey Nebo. I'm the responsible engineer for the liquids CAD as well as the whole system CAD.
To start off, we're going to do an engine overview. From there, we will break down into our subsections. Those subsections being the injector, the igniter, the fuel grain, the case and liner, the nozzle, and the ground harbor. And then we will wrap up with a system review.
Awesome. So what you're seeing here is a launch performed by Virgin Galactic, and what's important about this is that this is a hybrid technology that was done just a few months ago, and this was actually civilian transport. And so what's interesting about this is that, like I said, it is hybrid, but you may be asking yourself, what is a hybrid? Well, a hybrid is a combination of both solid and liquid rockets. And so what we do here on campus is we use liquid test engines as well as solid test motors. And so a liquid is a combination of both using two separate phases. In this case, we're using a liquid oxidizer as well as a solid fuel. And so what's really cool about this is that there are companies that use hybrids in industry, such as Virgin Galactic, like we just saw, as well as Firehawk Aerospace and Hyperspace, which are both defense contractors. And so hybrids can be used for different mission objectives, as well as civilian transport, which is really, really cool. So what we're trying to do here at Embry-Riddle is provide some founding, some knowledge, some base for hybrid technology here on campus, since we don't currently have that. And we would love to get our students into industry pursuing hybrid technology.
Now, Embry-Riddle currently provides a really unique hands-on experience for students, and that is in terms of the rocket engine demonstrators. Currently, we have a solid demonstrator as well as a liquids demonstrator on campus. For the liquids demonstrator, students get to interact with test cell 3 on the Kairos engine, and for solids demonstrator, students can interact with Fire Lizard on test cell 2. Now, currently, there is no active demonstrator for hybrid technology to allow students to bridge the gap between what they learn in class and what they can do with their hands in person. This leads to our problem statement, which says that we have identified Embry-Riddle's gap in its rocket-based curriculum, especially as it pertains to hybrid technology. In order to address this issue, Issa is going to talk about our top-level system requirements.
Thanks, Bree. These are our top-level system requirements for the engine, our solution to the lack of hybrid technology on campus. First, our engine must feature two-phase propellant. As Noah said, we'll be using a liquid oxidizer and a solid fuel. Next, during testing, our engine will pass this requirement by achieving 250 pounds force of thrust within 10% deviation for at least 1.5 seconds. Our subsystems of the engine that Bree introduced comprise these different sections of the engine. Seen here in our engine overview, we'll split into the injector, which Noah, Joey, and Kevin will discuss. Next, Finn will introduce the igniter. Then Noah and Winona will introduce the engine case, liner, and fuel grain. And Bree and I will discuss the nozzle. Finally, Finn will conclude with the ground hardware. Each subsystem has derived requirements that come from the top-level system requirements. That means that the whole engine contributes to meeting these requirements altogether. To look at a concept of operations for this engine, this is the setup of how we'll feature the two-phase propellant system. First, during testing, we'll send liquid N2O or nitrous oxide through a main oxidizer valve from a dewar and send that through the injector. That will go to proximity of the igniter and the fuel grain, where we will start combustion. After good combustion, we will pass that down and begin hot firing. And ideally, we will see Mach 1 flow at the nozzle, which means that we have optimized the flow and can realistically achieve our thrust goal of 250 pounds force. Now that we know what the engine needs to do, Kevin will discuss the specifications and analysis using a hybrid rocket analysis program that gives us the derived requirements for each subsystem.
So now that we've contextualized the hybrid rocket motor, we're going to be looking at how we are going to design an engine that will meet the requirements specified earlier. The way we did it was a two-part thing. We used an Excel program that we've created ourselves in conjunction with HRAP. HRAP is a MATLAB script produced by Robert Drew Nichol at the University of Tennessee. It allows you to design hybrid rocket engines, and this program has helped design, and those engines have been tested to completion on a scale of about 10 to 100 different engines have been using this program. So the first thing we do is we take a look at these Excel outputs that we produce for Excel. These outputs are in our massive calculator, and we take these as a preliminary guesstimate that we then plug into HRAP. Right here you see the HRAP's main screen. This is where you put all of your inputs into HRAP. You answer a bunch of questions, and we take this, we run it through an iteration, where we then get an output, which is seen here in HRAP. This output gives you your main requirements, so things like your thrust, your chamber pressure, your pressure drop, and we take all of this data, and we then run it through and back check it with our own Excel program. And we see any of the discrepancies, and then we will redo our initial questions in Excel, which we get new outputs that we then put into HRAP, and we iterate through the circle until we hone in on a HRAP program that meets our requirements. This right here is what our Excel outputs look like, and we take these and compare them to HRAP. Right there is a big transient table that produces transient graphs like you saw in the HRAP one. It's just not as clean as HRAP. So here you can see the HRAP thrust simulation of our optimized script, and you can see that we hit that 250-pound thrust requirement. And so to meet this requirement, we had to derive requirements. And the way we did it is we had fuels as HTPB, our oxidizer was nitrous oxide. We had a burn time of 20 seconds, an OF ratio of 8, which is our ideal OF ratio. We have a mass flow rate of fuel of 0.15 pounds per second, a mass flow rate of oxidizer of 1.2 pounds per second. We then also have a chamber pressure of 375 psi with an expansion ratio of 4.5, followed by our throat band of 0.82. All of these were derived using HRAP injection with Excel to back the performance of HRAP, and we use these to solve for all the other subsections. Now we'll be talking about the injector. And the injector is in the forward section of our assembly. It's what allows you to transfer liquid nitrous oxide into the grain while also atomizing it and spreading it throughout the grain length. Joey will now be discussing this.
Thanks, Kevin. The injector is made up of two main components. In order to meet our top level requirements, we need to integrate with test cell 3. We also need to flow nitrous oxide through the injector onto the solid fuel grain at a mass flow rate of 1.2 pounds per second, with a maximum mass flow deviation of 50% from the front to the back of the grain. Let's take a look at the injector. It's made up of two main components, the backplate and the faceplate. Fluid flows through the faceplate through 15 holes in an inclined showerhead configuration. The faceplate and the backplate are made of steel. These two parts are sealed together with O-rings, and the backplate connects to the feed system with a -8 boss fitting. Let's take a closer look at the faceplate. So like I said, there are 15 holes that allow the liquid to flow through onto the fuel grain. These are in an inclined showerhead configuration with 3 points of impingement along the length of the fuel grain. At an angle of 83 degrees, we have our first point of impingement at the top of the fuel grain.
So why do we have these angled holes? And the reason why is we're trying to decrease the gradient of the OF ratio along the grain. So what does that mean? You see in this colorful image, with hybrids, they have an inherent inefficiency, and that is having your OF ratio change throughout your grain. At the top of your grain, you have a lot of oxidizer and little fuel, and at the aft section of your grain, you have a lot of fuel and little oxidizer. And you want to try to mitigate this to have even burning, so you don't have burnout at the top of your grain, and you also don't have unburned propellant at the end of your burn. And so how do we decrease this gradient? And the way we do that is instead of having a regular showerhead, we have 3 different impingement points like Joey discussed earlier, that occur at different sections of the grain to allow us to have a lower gradient of the OF ratio, therefore giving us a higher percentage of the ideal OF ratio at the end of the grain. Right now, we're looking at around 100% of the OF ratio, of the ideal OF ratio at the top, and about 52% at the aft. This is something that we've compared to another university who's done analysis on ideal aspect ratio hybrid motors, and they have derived that this is what they were able to visualize with their spray patterns. So this is the goal that we're trying to hit.
Now, in order to integrate our injector, we'll first place the O-rings onto the back plate. We'll then bolt on the face plate with 6 440 screws. Sorry, bolts. We'll then take that whole assembly and bolt it onto the thrust plate with 3 1/4 20-inch bolts.
So now, how do we go about getting the 1.2 pounds per second for the oxidizer flow rate? So what we first looked at is we looked at the ideal OF ratio for HCPB and nitrous oxide hybrid. And you can see that around 8, we have the highest performance as indicated in ISP. We use the mass flow rate of fuel equation listed above to solve for the mass flow rate with the density of the HCPB, the regression rate that we've assumed in literature, and then the geometry of the port. We then take the OF ratio with the OF known, the mass flow rate known of the fuel, and the only thing left to solve is the mass flow rate of the oxidizer. We do a simple solution, we get a mass flow rate of 1.2 pounds per second, therefore verifying our HRAP simulation along with our Excel. Here you can see the HRAP simulation of the mass flow rate of the oxidizer. You can see that we are able to hit that 1.2 pounds per second throughout the full duration of the burn, meaning that we hopefully can have an 8 OF ratio throughout the whole entire 20 seconds. So now that we've talked about this 1.2 pounds per second mass flow rate, how do we actually design an injector that will give us a mass flow rate of that? The way we did it is we used something called the orifice equation. This is an expanded version where I took the total area and solved and moved it down to a number of holes and then the diameter of those holes. I then also introduced a delta P, which I expanded out to the pressure above and the pressure below. The pressure above is the pressure of the liquid nitrous oxide flowing into the injector, where the pressure below is the chamber pressure at 375. We then take a diameter of orifices. We assume a diameter of 1 or 0.39 inches. And then our port area ratio is the ratio of the port of our dash 8 fitting to the total area of the holes that the NTO is flowing through. And then we also introduce the properties of nitrous oxide, which are just characteristics of nitrous oxide at a certain pressure and temperature, like coefficient of discharges of the geometry, expansibility fluid density, and then the next slide. So now that we have those, we put all those into the equation while assuming our diameter, and we are going to solve for n, the number of holes. And so we solve this equation, we find when n is equal to 15, or when we have 15 holes, that the left side of the equation is equal to 1.2 pounds per second, therefore meeting our requirement of 1.2 pounds per second for the mass flow rate of oxidizer, meaning that our injector is sized to have 15 holes with a diameter of 1 millimeter or 0.39 inches.
Now, in order to make sure that we don't have any fluid flow underneath the O-rings, we did an ANSYS simulation of the faceplate. First of all, we have fixed supports at the 6 bolt holes. We have a cylindrical support on the circumference of the faceplate. And as for the load, we have an area of 550 psi inside the area created by the first O-ring. Now, put into ANSYS, we found a maximum deflection that is corresponds with the tolerance set by the Parker O-ring handbook, meaning that we're not going to see any leakage under the first O-ring.
So now that we've overviewed the CAD model and how we designed the injector, now let's talk about how we're going to manufacture it. So what we're going to do is faceplate and backplate will both be machined out of 303 stainless steel. The faceplate will be done on the water jet, followed by some manual machining. where the backplate will be used on the lathe and possibly CNC lathe. Right now there is a prototype of the manufacturing plan, which is an aluminum piece that we're right now designing. There's an aluminum faceplate right there that we are trying to verify that we can make these holes to 1 millimeter without breaking them, as that was a concern in the PDR. So then after that, we're going to assemble both the faceplate and backplate with the O-rings, the bolts, and a little bit of lithium grease.
Next, Finn will talk about the igniter.
So the igniter is the most important component when it comes to startup. This is going to be the biggest and most difficult aspect of the hybrid. First things first though is what are the requirements for it. It needs to have an exhaust temp, or produce an exhaust temp of over 1,000 degrees Kelvin. It also needs to fasten and adhere to the solid grain. We don't want this to be moving around before or during operations. Now what's the design of the igniter? The igniter placement is going to be at the top of the grain, so in the figure on the left, you can see the top of the grain is going to be concentric with the grain, and then the inside diameter of the igniter is going to be 0.75. Now these dimensions are due to change once we start testing, because testing is going to be the biggest part about finding the igniter duration that we need for a smooth startup. Now, why does the igniter duration matter? It matters because what we want and what you see on the left is a steady state hybrid. We have a section near the grain where it's fuel rich. We have a flame zone where your OF, what Kevin was talking about, matches, and we get good combustion, and you have a section of oxidizer rich. For us specifically, our fuel, which is HVB and MDI, it has a pyrolysis point of less than 1,000 degrees Kelvin. Pyrolysis is just where the chemical bonds actually start to break down. And what we want to see is where we're getting at sublimation, or the vaporization of the grain. Now, how can I prove that? We use a simulation on campus called ProPEP, where we use our solid motors. We're using Samba 1.0, which I discussed, and it's going to output an exhaust temp of about 2,500 Kelvin, which is well above the 1,000 degrees Kelvin that we need. How are we going to manufacture the igniter? We're going to be using the same process that we use on campus, however, some differences. Specifically when it comes to the mold, we have to make new 3D printed molds, where we then fill with a 2-part silicone mold, which is what you see in this picture right here. Then we'll use our regular procedures on campus, using sample 1.0 as the propellant, mixing that and then letting it cure. After we cure it, we're going to prep the grain. So using the grain cutting cell, making sure that these match our sims, so when we're doing testing, when we're really figuring out the duration of it, we don't have any confusion over what works, what doesn't work. Next, we're going to be talking about the fuel grain with Winona.
Thank you, Finn. I will be discussing the fuel grain, which is located in the center of the engine, in between the liner and the case. There are 3 main overarching requirements for the fuel grain, which are that it needs to integrate within the engine liner and the case. It must be a solid fuel to go with our 2-phase propellant types to meet the hybrid standards, and it must be able to generate a thrust of 250 pounds force, which is then met with the mass flow rate, which needs to be at least 0.15 pounds per second. Then going into our fuel grain geometry, we chose a base grain geometry, which is the current geometry used on campus for most of the solid motors that they test. This is going to be the hollow cylindrical shape with the 1.75 inches in the inner diameter and the 3.239 inches outer diameter. The outer diameter is set by the casting tube that we are purchasing from Always Ready Rocketry, and that's going to be able to keep our engine grain at this outer diameter. The fuel grain composition is going to be made out of 72% HTPB and 20% aluminum additives. This is going based off of our research done with the hybrid combustion analysis book that we use for most of our calculations, and this allows us to be able to generate that 250 pounds force thrust that we are trying to achieve. And another key feature in this composition is the MDI, which is the curative that is going to allow for it to cure into a solid state. In order to generate how much MDI and curative is going to be needed to get to a solid state, I used the RDL documentation and went through to calculate the equivalent weight of the curative, which then allows us to plug back into the weight of the curative equation to calculate a 7.2% weight curative. This essentially means that in order to be able to have our propellant curing to a solid state from its HTPB liquid state, we need to have at least 7.2% MDI of the total propellant, so that it will be able to fully cure in that solid phase. Next, going through to calculate the efficiency of the grain, in order to create the most optimal length for the grain to be able to generate this 250 pounds force, we went through and used the length equation that's given from our Stanford Academics PDF, and that being able to plug in all of our known values of the total mass of the oxidizer and the density of the fuel, our optimal OF ratio, and the diameter of the final port and the inner port, we then are able to get the length of 14 inches. We then plug that into our volume equation, and this allows us to get the total volume, knowing all of our givens of our propellant, and that will allow us to calculate the total mass, which is going to be around 3.11 pounds. This will allow us to be able to fit all of our propellant inside the engine nicely and to create an optimal thrust ratio. Next, in order to calculate the regression rate, we need the regression rate because in order to calculate the total thrust of our engine, we need the mass flow rate of the fuel. The mass flow rate of the fuel is dependent on the inner port diameter and the regression rate. The regression rate is based off of the regression rate coefficients and exponents given in a PDF based off of the performance of N2O and HTPB engines. In order to fully generate a more accurate ANN values, once we have completed testing and gone through, we will then replace the ANN values with our actual configuration ANN values, because those are experimental. The inner port the diameter of the port was calculated through this equation, also given by the Stanford lecture PDF. And plugging all of those back in, we then get a mass flow rate of 0.19 in pounds per second, and a regression rate of 0.04 inches per second. The image that is shown on the bottom left-hand side of this graph is what the fuel is going to look like after a burn test. This is basically showing that the grain is not fully going to be burnt through by the end of the test, ideally, with our optimum OF ratio that Kevin explained earlier. Here is our mass flow simulation that we got produced from HREP, and it shows our mass flow rate of the fuel at the times 5, 10, and 20 seconds once we have for each of the tests that we are aiming to perform. And we have reached the 0.15 minimum requirement. We are then going to be mixing the propellant on campus with the current standards set in place with the EHS rules, and we're going to be using the mixing apparatus shown. We will then be pouring it into the casting tube setup in the second image, and that will allow for it to fully cure to the exact dimensions of the 1.75 inner diameter and the casting tube outer diameter 3.239. And then finally, it will then be prepared and it will look similar to the last image. Then that's what the fully cured solid fuel will look like. Next, Noah and I will be discussing the engine case and liner analysis.
Awesome. Thank you, Renata. So, like Renata just said, I'll be going over the engine case as well as the liner. So, to start off, we need some requirements, and we need to fulfill some requirements that are set by our top level requirements. And these are being able to integrate with the nozzle alongside the injector, in addition to being able to withstand 375 chamber pressure, or 375 psi of chamber pressure, our combustion temperature of 6,000 degrees Fahrenheit, as well as be in accordance with ASME standards, which is having a factor safety of 2.4. And so, breaking down the engine case and the liner, we're going to start off with the outermost layer, which is the engine case comprised of 6061 T6 aluminum. Following that, going a little bit more inwards, we're going to have a phenolic engine liner. This acts as an insulatory material against high temperature gases, as well as just flames in general, high temperature flames and combustion in general. Next up, we have our phenolic pre-combustion chamber insert, which is even more insulatory material, so that way the engine case does not heat up too much. Following that, we have our casting tube, which Winona was just talking about, highlighted in the yellow here. And then we have our post-combustion phenolic insert, which is also another insulatory material to make sure that we do not overheat the case to to withstand that 6,000 degree Fahrenheit temperature requirement. Following that, we're going to look down at the nozzle. We have 6 1/4" 20 brass bolts, and we have our fuel grain HTPP as well as our ensemble igniter, which Finn had been talking about, and we have 6 more 1/4" 20. These are grade 5 steel bolts, and I'll be breaking that down as to why these are 2 different materials. So just a general overview of the size of the engine case as well as the engine in general. We have a 4.5" outer diameter with 3.5" inner diameter. These will be integrating with our bought parts from our manufacturer, like Winona had said, always ready rocketry. So this is our engine liner dimensions. This will then be integrating with our casting tube and our fuel grain. So these dimensions are set by manufacturers. They have tolerances on them so that they can be friction fit together with one another, and we won't have any issues integrating regarding this particular section. So to start off with our engine case stress calculations, we need to determine how are we going to get this factory safety of 2.4, how are we going to meet it? So we can use this factory safety equation to solve for our factory safety using yield stress, our wall thickness, as well as our chamber pressure and the internal diameter of our case. And so when we plug in all these numbers, we get an astounding number of 30.47, which is significantly higher than that of 2.4. So we are by far surpassing the safety requirements required by ASME. And so the reason that is the case is because we're using 1/2" wall thickness, 6061 T6. We could go a lot thinner, but then our factory safety would go down a lot, and that is not what we would ideally like. So with a factor of safety of 30.47, we can then plug it into a margin of safety equation, yielding a 11.7, which is abnormally high, because traditionally margin of safety is within the scale of 1 to 2, maybe 3 to 4 if you're on the higher end, although this is once again due to our extremely high factor of safety, so this plays into our margin of safety equation. So next up, we have to talk about bolts and just the overview and general knowledge about what's associated when calculating stress that these bolts will encounter during hot fires. So what's most important in this equation is that the number of threads engaged for the injector is twice that of the nozzle. And so the reason I did that is because we want the nozzle to be the first thing to fail if something does go wrong regarding the engine case or during a hot fire. And so we want to make sure that the nozzle essentially gets ejected out, or the bolts shear that are holding the injector or the nozzle in. And that is because that will mitigate most of the issues that could protrude from something going wrong. So in order to make sure that that is going to be the case, I did some calculations on the bolts that are integrating with the injector as well as the nozzle. So to find the force on the bolt, I can use this equation here, shown on screen. We're using 6 1/4" 20s, like I had just said. And so we can find that we're going to be experiencing 600 pounds of force on each bolt. Following that, we can plug that into an axial stress equation. And this is stress from the inner wall this is inner stress, like chamber pressure, that will be going down the length of the grain, or the length of the engine case. And we can then calculate bending stresses that the bolts will experience using von Mises bending stress equations. And then essentially we can solve for transverse shear stress. And so what's most notable is that the transverse shear stress for the injector here is essentially half that of the nozzle due to the number of threads that are engaged with the nozzle. And so we can then do the same thing for the nozzle, use the same equations and find out all these different stresses, and note how the transverse shear stress is double that of the injector. And so that essentially proves that the bolts in the nozzle will fail first rather than those of the injector. And so Winona will be talking about the heat transfer next.
Thank you, Noah. In order to go through and calculate the heat transfer, we went and analyzed the convection coming from the combustion, going through the fuel grain and out to the liner, and finally to the case, which we assumed was thermally insulating. This will allow us to create a resistor network of the heat transferred per unit length with the following equation and the givens that we have gone through and calculated, such as our temperature of the combustion, temperature of the case which we went through and calculated. We are assuming that the convection coefficient is going to be infinity, just to have conservative values. And we went through and then plugged that number then into the temperature equation to get a temperature of the case on the outside. And once we were able to go through and calculate where the grain was fully burned and that it was going through the liner with no more grain fuel remaining, we were able to calculate a temperature difference of 12.85 degrees Fahrenheit, so that it resulted in the case temperature being 82.85 degrees Fahrenheit. This is unlikely, as I had mentioned earlier. There should be grain fuel remaining throughout the entirety of the case, but in worst case scenario, the main difference is 12.85 degrees Fahrenheit. Next, we are going to look at the pre and post combustion chamber sections. In order to calculate this, we have a phenolic insert that is going to be placed in the pre and post combustion sections to minimize the heat transfer to the case so that the case will be able to withstand the combustion temperatures. So we have the convection going from the combustion, going through the phenolic insert, and going through the liner to finally to the case. Again, with this same equation, we have the amount of heat transferred to the case per unit length, going through calculating the temperature of the case, and that gives us a temperature difference of 2.27 degrees Fahrenheit at 20 seconds, which is our maximum time that we are going to be, the case will have to endure the temperature for. Next, Bree and Issa will be talking about the nozzle.
Thanks, Verona. Seen here, the nozzle subsystem is located in the aft end of the engine. First, we'll look at the requirements that have been derived from the top-level system specifications, as well as the HRAP analysis they have performed. In order to contribute to the flow of the engine, our nozzle must integrate with the engine case. The thrust requirement can be met and contributed to by our nozzle by featuring an expansion ratio of at least 4.5 and a combustion pressure of 375 psi. Finally, the nozzle material must be able to withstand the tests that we will perform, specifically the higher thrust during the second and a half burn time, and then for the 5, 10, and 20-second burn times as well. Now, to introduce the dimensions of the nozzle is comprised of a graphite and phenolic throat insert. This we will be purchasing from Loki Research, which will be made for a 54mm engine case. And in order to make it fit with our 98mm engine case, we will create a steel converter which will increase the outer diameter of the nozzle to fit that case and continue the converging and diverging angles. These angles are directly from the manufacturer as the converging and diverging half angles. And in order to meet the requirement of our thrust that Kevin introduced with HRAP, our throat diameter will be 0.82 inches. The steel converter will continue that diverging angle, so we achieve an exit diameter of 1.75 inches so that we can optimize our flow, ideally meeting our thrust requirement of 250 pounds force. Here you can also see the CAD. The nozzle insert is sunken in, and we'll be using a smaller O-ring to seat the nozzle insert in the housing, as well as 2 larger O-rings between the housing and the case itself. Seen here is the integration from the nozzle sub-assembly into the case, using those O-rings and 6 quarter 20 bolts. As Mel mentioned, they are brass, so that we fail at the nozzle if we fail at all. And the dimensions for those bolts are seen here. Now, Bree will discuss the expansion ratio and combustion pressure specifications.
Thank you, Issa. The first design requirement for the nozzle states that the nozzle must have an expansion ratio of at least 4.5. Now, the expansion ratio is the ratio of combustion from the throat of the nozzle to the exit of the nozzle. From there, we can use the equation for expansion ratio as seen here, which is comprised of dimensions as well as assumed values such as the ratio of specific heats. Now, you may notice there's an unknown term in this equation, and that unknown term is PE. Now, PE is the pressure at the exit and can be classified in one of 3 different ways. The first way is an overexpanded case, where the pressure at the exit is less than that of the surrounding atmosphere. This reduces the amount of thrust generated by the nozzle. The second case is an underexpanded case where the pressure at the exit is now greater than that of the surrounding atmosphere. Again, this reduces the amount of thrust generated by the nozzle. The last case is the ideal case where the pressure at the exit equals that of the surrounding atmosphere. This will allow the nozzle to maximize the amount of thrust being generated. Therefore, we set our pressure at the exit equal to that of the surrounding atmosphere, which for here in Prescott is approximately 12.19 psi. From there, we can go ahead and solve, and we get that our expansion ratio is 4.7. This means that the area of the throat will be 4.7 times less than that of the exit area of the nozzle, and thus meeting the requirement as set by EDRAP. The second design requirement for the nozzle states that the nozzle must be able to withstand a chamber pressure of 375 psi. In order to determine if the nozzle can in fact withstand this amount of pressure, a stress analysis was performed on the surrounding exterior. Now, according to ASME standards, as Noah previously mentioned, a factor of safety of 2.4 is required for a pressure vessel that is under 500 psi. From there, based on the dimensions of our nozzle, we can use the factor of safety equation. And when we plug in all of our values, we get that our factor of safety for the nozzle is 71. Turning this into a margin of safety, using the margin of safety equation, we get a margin of safety of 28, which is significantly high, and thus meeting the requirements set by ASME standards, meaning yes, the nozzle will in fact be able to withstand 375 psi pressure. The last design requirement for the nozzle states that the nozzle must be able to supply a constant thrust for at least 1.5 seconds of the total burn time. Now this becomes an issue with erosion. Erosion is the process a material will undergo when exposed to high temperatures, where it will disintegrate and go away. As you can see in this image, this is an image of a graphite nozzle that has been hot fired. That circle in the middle, the blue one, is where the throat diameter initially was, and in the red circle is the diameter post-testing. Now this increase in the throat diameter will reduce the amount of thrust generated by the nozzle. So we want to make sure to try to avoid this. Now putting this in terms of our systems, as Issa previously mentioned, the initial throat is 0.82 inches. We then contacted the manufacturer for data on erosion rates, and got this quote that says for a 5-second burn time, they expect us to see an erosion rate of between 1 to 2 thousandths. We then took this erosion rate given to us by the manufacturer, multiplied it up to our maximum burn time, which would be 20 seconds, and added it to our initial diameter. And when we did that, we got a end expected diameter that the manufacturer expects us to see due to erosion. To validate this number, we then spoke to the RDL solids team, who have experience with graphite nozzles. And we got this quote, that for a 7 to 8 second burn time, they expect us to see an erosion rate of between 1 to 10 thousandths of an inch. Now, one important note is that solids burn a lot hotter than hybrids, therefore the erosion rate seen by the solids RDL people will be a lot higher than that the hybrid engine actually experiences. And then from there, repeating the same process as we did with the manufacturer, we took this erosion rate, multiplied it by our max burn time, which again is 20 seconds, and added it to our initial throat diameter to get a final eroded diameter that the RDL expects us to see of 0.85. From there, we then plugged both these values into EDRAP and ran a simulation. And as you can see, for this 5 second, even though the nozzle will be eroding, we are still above the 250 pound force requirement. And same here for the 10 second. And now in the 20 second, we are right on that line, which meaning that the nozzle for the first 5 second and 10 second burn time will be able to supply a constant thrust of 1.5. And once it gets to a 20 second, the nozzle that is the max life. So we will be powering down and we cannot go past that 20 seconds of burn time without deviating from the set requirements.
Now that we know how our nozzle should look and perform, we can discuss the manufacturing process. As I said, we're purchasing the nozzle insert from Loki Research. From that part, we can create our steel converter, which, as I said, will continue the converging and diverging angles and achieve our exit diameter. Finally, when it comes to assembly, we'll be using that O-ring in the center and RTV in these locations to adhere the nozzle insert and the nozzle converter together. And as an example, this was a previously used solids research test nozzle sub-assembly, which also utilized the same style. So to conclude, this is our nozzle subsystem, which is the last subsystem of the engine itself, which means we can bring the engine back together, and it will be supported by the ground hardware, which Dan will now discuss.
So ground hardware, how we're integrating onto our test cell. First things first, we need to support the engine or requirements. We don't want any preload on those load cells. We also don't want to deflect the thrust plate before we have thrust. And then finally, we need to integrate into the test L3 DAC system. It's academia. We want to be able to see what's actually happening in the engine and learn from it. To give you a quick overview of how we're integrating into the test cell as a whole, as you can see, I'm going to start from the right and work my way around. We have the DAC cabinet, known to us as Pixie. Then we have the feed system, the doer that we're going to have that Issa talked about previously, our structure, our thrust structure, and then finally our engine. Now, more specifically, what our ground hardware looks like, how we're integrating into it. We have our feed system. Luckily for us, Kairos, the liquids demonstrator, which we discussed at the beginning of the presentation, we're able to use that feed system. And then we have our own thrust plate, and then we use a stand where that stand can be any V stand that we have on campus, where we have this accessory put on place to protect it, and also if we wanted to add any rollers or anything else to help be more versatile for different sized engines. This will be made out of 6061 aluminum, and it's an 1/8 inch thick. Now, how are we going to make all this? Most of it's water jetting, which is amazing because that means that our thrust plate is already done, this picture that you see right here. After we water jet the accessory, however, we need to bend its flanges and then finally bend the final V angle into it. Other than that, that's all of the ground hardware. We're now going to move into system review, which will give you a quick overview of exactly what we talked about today, as well as give you a little bit of insight on what we're moving forward into. The first thing that's going to get discussed is our test plan, where, as you can see, the first 3 are all of our subsystem tests, where we start with the igniter, where we're looking at mainly using test L2. We're looking at figuring out the distance from the ejector using igniter tests. That's going to be specifically on test L2. And then fire duration, where we're using solid fuel melt tests. Then moving on to injector, where we'll be using test L3, where we're looking at spray pattern using water flow tests. And then finally, mass flow rates using cold flow tests. Then finally, solids fuel, where we'll be using the prop lab to do density measurements using volume water displacement on campus. And then, as the entire system, once all of those tests have been passed, we'll do our hybrid engine test campaign, which will start with burp tests for ignition. This is proving that the igniter works fully. And then moving on to our 5-second and our 10-second, which will verify our regression rate math and our erosion rate math. And then finally, our 20-second burn rate, our 20-second hot fire, which will verify our steady state.
So our drawing package will be split up into 6 assemblies. The top level one is the full assembly. And inside of that is the subsystems that we've talked about before. Now, all of our drawings are in review currently with Professor Garrick, except for the nozzle insert, which we are ordering. As we've proven in the presentation, all of our requirements have been met.
Here is our semester timeline overview that we are going to be trying to accomplish within this semester. First of all, we are currently working on our system updates with our CDR that we are currently presenting to you right now. We will then be going over our drawings, which are in review with Professor Garrick, as Joey has just mentioned. We will then be ordering our supplies as soon as everything has been approved and we get the go-ahead to be able to order them. Then, within our test plan section, we will be conducting individual pre-approved TRRs to be able to ensure that all of our subsystems are guaranteeing their requirements and fulfilling their components within manufacturing and being able to fabricate them corresponding with the test plans, and whenever those individual pre-approved TRRs are able to be completed and approved on. Once we have been able to finish the fabrication process within each of the different subsections, we will then complete our engine testing and our engine TRR before testing. Then we are going to complete the testing with the aims of a hot fire on April 15th. And then once we have finished our hot fire, we will continue to analyze all of the data that we are going and compiling our report for symposium and our final report. Here is a project estimate. We are currently at around $2,210 with our current capstone budget is $1,550. As you can see here are each of the different breakdowns for our subsections and how much they are going to cost. Currently, we have applied for URI and we are hopeful that we will get it. However, without URI, we are still in the negative around $600, $700. If we are not able to get URI, we have completed the crowdfunding with Steve Babinski to be able to set that up, and we have sent that out to many people, and we have all of that currently writing on.
At this time, we'd like to thank both of our professors, Professor Garrick and Dr. Adams, for all the assistance that they provided for this project. We'd also thank Dr. Sarker for all the assistance with stress calculations. We'd like to thank Scott from Loki Research for all the help with the nozzle. And we'd like to thank Ray from NASA for all the help with this project. Are there any questions?
3 minutes.
I know you guys have an
Yeah.
exam, and my wife just showed up with my phone, and so I'm gonna want to get out of here as well. I took a bunch of notes, but I think certainly it was a well presented presentation. There's a few technical things that I'll discuss with you, but I think it came across quite well. I think the organization was good. I like that, the system analysis came through well. The way that the analyses were presented was good. I'll follow up, I guess, probably Wednesday with, and have you upload next slides?
Yes.
Great.
And also you can, so I
Great.
Once I follow up with the video too.
Where's the?
Okay.
Thank you for coming.
Thank you.
What's up, guys?
Thanks, guys. I mean, yeah, I can definitely look at tests for that, but I don't think that would happen. That's a really good concern, though. So I'll definitely look into it.
And then I have some questions. Are you not using it for cherry?
Yeah.
Okay.
Yeah, just because they didn't want me to put any of those in the slides.
That
Okay,
fixes
you want
it.
to ask me right now? Okay,
Yeah,
right now.
right now.